We saw in the previous example that even lossless joints can lead to trouble because we might end up with decompositions that are not what we will call dependency preserving. So let's start with an intuition for what dependency preservation means. And then we'll add some formalism to define it crisply. So, intuitively, a dependency preserving decomposition means the following is true. If we have decomposed R into, say, 3 parts, X, Y, and Z, and we enforce the functional dependencies individually on each of the parts. In other words, we enforce the functional dependencies on X, we enforce the functional dependencies on Y, and finally on Z. Then we would like that alone to be sufficient to ensure that all the functional dependencies that hold on the entire relation R also hold on the decomposition. If this is true, then we have avoided the problem number 2 on our list earlier. So that's the intuition. We are just going to locally apply the functional dependencies to each part of the decomposition. And we hope that's enough to get us what we would have had if we had forced the functional dependencies on the full table. So now let's define some terms so that we can formalize this idea. First, we define the projection of a set of functional dependencies, F. If R is decomposed into X and Y, and the projection of F onto X, which is denoted as F sub X, is the set of functional dependencies UV in F plus, in other words, in the closure of F, such that all the attributes U and V are in X. So think of taking F and its full closure, which, as you know, is exponentially big, but that's okay. And then just take from that full closure only those FDs that reference the variables in X. And that's F sub X, or F projected to X. It is important that you do this on the full closure of F, not just on F, as otherwise you don't get this right. So a projection of a set of functional dependencies is anything that could possibly be applied to the columns in the decomposition. And now we can define what a dependency preserving decomposition is, given that definition. A decomposition of R into X and Y is dependency preserving if F sub X union F sub Y closure equals to F plus. This is just another way of saying what we have said before. If we consider only the dependencies in the closure that can be checked in X without considering Y, and that can be checked in Y without considering X, these together would imply all the dependencies in F plus. So that's the formal definition of a dependency preserving decomposition. Now, some notes about the dependency preserving decomposition. As we said, it's critical to consider F plus in the definition. So let's have an example to think about this. Let's say we are given our table A, B, and C, where A determines B, B determines C, and also C determines A. Let's say we are going to decompose this into AB and BC. And we want to know, is this dependency preserving? Particularly, is C determines A preserved by these projections of dependencies? Well, obviously C is in one table and A is in a completely different one. So we might think that's not really dependency preserving, but let's be a little bit more careful. F plus, the closure of F, contains F, and it also contains A determines C by the transitive rule because we know A determines B and B determines C. It also contains B determines A by the transitive rule because B determines C and C determines A. And it contains C determines B, again by transitivity. So looking at that subset of F plus, we can say that F projected to A and B contains the following things. It contains A determines B because that's in F. It also contains B determines A because that's an F plus. Similarly, F projected to B and C contains B determines C from F, and C determines B, which was in the closure as well. So FAB union FBC plus contains B determines A from FAB, and C determines B from FBC. So when we take the closure of just those two things by transitivity, we also have C determines A. So this is a case where it does appear to be dependency preserving, or at least we know that C determines A is preserved. Note that it's not obvious at all until we form the closure F plus in this case. But it does come out when we form that closure, as you see here on the slide. So how do we do our decomposition into BCNF? Let's go through this formally. We will consider a relation R with functional dependencies F. First, we check if R is already in BCNF. If not, then we pick some functional dependency, say A determines B, that violates BCNF, meaning that it's not a trivial one, and the left-hand side A is not a superkey. Then we will decompose R. We do that by first computing the closure of A, and then we create two relations, R1 consisting only of A plus, and R2 which consists of all the attributes not in A plus union with A. Then we compute the FDs that are relevant for R1 and R2. We now go back to step 1 for R1 and R2 separately. And we stop when all relations are in BCNF, or they only contain two attributes or fewer. Remember that relations with two or one attribute are already in BCNF form. Now, BCNF is a lossless joint decomposition that is guaranteed to terminate since we have a finite number of columns that we need to partition. So let's take an example. This is our contract example that we had from before with CSJ DPQV, with key being C, JP determines C, SD determines P, and J determines S. So let's start with the violating functional dependency, SD determines P. Why is that a violation? Well, SD is not a key and it's not a superkey. So that means we'll need to decompose. We'll decompose that into SD plus, which is just SD and P, and the union of SD and everything else not in the closure, meaning CSJ, DQ, and V. Now, the relation SDP is already in BCNF, but the other one is not. Why? Because of the violation J determines S. So again, we'll decompose it into JS, the closure of J, and CJDQV, which means everything else union with J in this case. So we now have three relations. We have SDP, where SD is a key. We have JS, where J is a key. And we finally have CJDQV, where C is a key. At this point, we terminate because our FDs are all satisfying BCNF. Notice how in this case, several dependencies cause the violation of BCNF. And in fact, it turns out that the order that we use them to decompose could lead to a different outcome. So there's more than one way to decompose a relation, and it is actually determined by the order in which we process these violating functional dependencies. Unfortunately, there's bad news. There may not be a dependency-preserving decomposition into BCNF, so we can always get to BCNF and be also lossless. Here's an example. We have the relation CSZ, where CS determines Z and Z determines C. There is no way to decompose this while preserving the first functional dependency. Yet it is not in BCNF because it violates the second functional dependency. So we have to decompose it somehow, which means we will lose our dependency preservation. Similarly, the decomposition of our contract table CSJDPQV into SDP, JS, and CJDQV is also not dependency preserving with respect to our functional dependencies. However, it is lossless because we follow the rules of BCNF decomposition. So here's a trick we could play. We could add JPC as another table to the collection of decomposed relations that we formed earlier. That would certainly allow us to check functional dependency JP determines C very cheaply, but it's actually redundant. The only reason we have this table, JPC, is just to check the functional dependencies and satisfy the requirement. We can actually recompute JP and C by joining the three originally decomposed tables back together on their keys and getting the full relation back, meaning that JPC by itself is a strictly redundant table, but it's one that we could use for dependency preservation. Without going into too much detail, this is how the third normal form works. We try to do our BCNF decomposition. We then potentially lose our dependency preservation. And we do these redundancy tricks to get the dependency preservation back. What we are left with is a bit of a mess that got redundancy embedded within it. We won't go into the details here, but what I want you to remember is that BCNF can always be done losslessly, but cannot always achieve dependency preservation. If we want to achieve dependency preservation, we can start adding in these dependency check redundant relations. But we'll introduce redundancy as a result, and we will need to keep track of that inside the application.